Okay, thanks for the very generous introduction, Mark. Good afternoon, everyone. It's a great honor to be here at the Computer Architecture Seminar. As what Mark has introduced, my name is Carole-Jean Wu. I'm currently a research scientist at SysML of Facebook AI Research. I'm very passionate about work in the intersection between systems and machine learning. My research at Facebook focuses on designing systems for machine learning execution at scale, such as for deep learning recommender systems and for mobile deployments. I chair the MLPerf recommendation benchmark advisory boards and co-chair the MLPerf inference. Today, I would like to draw your attention to an underinvested but very important area of machine learning. This is on personalization and recommendation systems. Personalized recommendation algorithms are widely and frequently used across many application domains. It is the task to recommend content such as books or articles to users in order to encourage more relevant and meaningful engagement. It is one of the most important deep learning workloads used to support various Facebook products as well as across the entire industry. If we take a closer look at the development of personalized recommender systems, lots of research has been done prior to 2010 with the focus on classical approaches using techniques such as content-based filtering or collaborative filtering mechanisms. At around 2009, machine learning-based techniques started to emerge with simple techniques such as logistic regression or gradient-boosted decision trees. It is worth noting that Yahoo Research started looking at the use of hashing techniques at around this time with a seminal ICML paper on feature hashing. Then at around 2015, we started seeing the renaissance of deep learning-based techniques for personalization and recommendation use cases. Since then, we continue to see the sizes of the deep learning-based personalized recommendation models to grow to much bigger sizes. We also see different deep learning components making their ways into these personalized recommendation models. For example, the large embedding tables, the attention layers, and the LSTM components. Personalized recommendation is by far one of the most important and fastest growing workloads at Facebook. Among the total AI training cycles, about 50% is devoted to recommendation systems. And for AI inference, that's 80%, with the remaining 20% for non-recommender use cases, such as computer vision or natural language understanding. Meanwhile, if we look at what the research community is designing systems for, things can look quite different. Here is the pie chart showing the papers published in top system conference in the past 5 years. We found that the majority of system researchers were focusing on building and optimizing systems for neural networks that recognize cats and dogs. Only 2% of the papers study recommender systems. Now, before we uncover why the underlying causes, let's first take a look at how recommender systems work. From a high level, personalized recommendation is the task of suggesting relevant contents to users. We start with hundreds of thousands of candidate items at the retrieval stage. And across the different stages of the recommendation pipeline, increasingly compute-intensive neural network models are used to produce more accurate content recommendations. We then come up with a rank list of items. For Facebook, this means ranking hundreds of thousands of items with large-scale models with billions of parameters in order to serve billions of users worldwide. Let's take a deeper look at how neural recommender systems work. Recommendation models typically have two types of inputs. First are the continuous inputs that are processed by a set of DNN layers. This is often implemented as fully connected MLP layers in the dense DNN stack. The second type of input are the categorical input features that are represented as multi-hot encoded vectors. Given the scale of internet services that use recommendation models, these vectors are not only large, but also incredibly sparse. One way to transform these sparse inputs into dense ones is to use these embedding tables. Entries of the multi-hot encoded vectors are used to index into rows within the embedding tables in order to read the low-dimensional embedding vectors. These vectors are then pulled together and combined with the output of the dense DNN stack. And finally, a predictor DNN stack outputs the probability of users interacting with the items. For example, given a user and book pair, the neural recommendation model is used to predict the likelihood of the user preference of the book. Now, when it comes to evaluating how effective the systems are for training and serving recommendation models, it is intuitive that ranking more items leads to better recommendation quality. And therefore, from systems perspective, what we want to focus on is to maximize system throughput. At the same time, there's a user waiting on the other hand for rank recommendation list. And therefore, we have a very firm latency target to meet in order to keep the users engaged. And therefore, from system design and optimization perspective, we have a latency-bounded throughput optimization problem to solve here. Here is the agenda for today's talk. Given the importance of recommendation and ranking use cases, we'll take a look at the unique system challenges brought by this class of deep learning workload. Next, I'll share with you the performance characterization studies across the diverse collection of recommendation model architectures running on modern AI accelerators such as GPUs and compare their performance on baseline CPUs. This will be followed by our recent work on DeepRecSys, a work that's recently published at ESCA 2020, before I conclude the talk with the next steps, work in progress, and some of the future work. Based on our recent deep dive into understanding these system design challenges for training and serving deep learning recommendation models, I want to highlight 3 unique characteristics for neural recommendation. First is the large embedding tables that come with irregular memory access pattern. Deep learning recommendation systems demand far more memory resources as compared to the neural networks that we are used to. Second is model heterogeneity. Across model architectures, there is a heterogeneous combinations of recommendation model architectures that we run at, for example, Facebook's data center fleets. Depending on the specific configurations of neural recommendation models, the models themselves can have a variety of features. The width and the depth of the MLP layers, the size and the dimension of the embedding tables can vary across these models. And some of the more advanced recommendation model can come with attention layers in order to capture temporal information in the data set. Finally, the performance variance introduced by the dynamic at-scale execution environment introduced some interesting design challenges. When these recommendation models are deployed to the production environment, we've observed non-negligible performance variance that can come from at-scale execution, such as the query arrival characteristics or different model co-location degrees. This can introduce different degrees of queuing delay depending on the execution styles, and sometimes this can lead to observable degradation in detail latency. Next, let's take a closer look at the resource requirement characteristics of the embedding tables. The embedding tables in industry scale recommendation models demand tens to hundreds of gigabytes of memory storage. This memory storage requirement is increasing exponentially into the terabyte scale. Furthermore, when we compare the compute intensity for embedding operations is orders of magnitude lower than that of CNN and RNN networks. Finally, the sparse vector lookup to the embedding tables leads to irregular memory accesses. Our recent study characterizes a collection of embedding table traces for our production recommendation models. We found that these recommendation embedding tables can introduce memory accesses that has poor data locality at the CPU's cache hierarchy. And this imposes significant stress on existing off-chip memory bandwidth and also motivate interesting novel memory optimization solutions for this particular deep learning workload. The second challenge faced for a recommender system is model heterogeneity, as what I've mentioned before. At the high level, we can generalize the collection of recommendation models into three major categories. Models in each category demonstrate distinct model architectures and varying parameter specification as described in the table. Within each category, there is a diverse collection of models. And in aggregate, they are about 200 different recommendation models running concurrently at Facebook's data center fleets. As what the table shows, the dimensions and the depths of the FC layers vary across the three distinct model categories. The number and sizes of the embedding tables are different for different use cases. Furthermore, the degree of lookups per embedding table operation is also unique, introducing different memory capacity and memory bandwidth requirements on the system. What this all means is that when designing systems for recommendation models, we have to keep in mind the model level characteristics requiring different optimization strategies. Furthermore, because of the model composition, the operator time breakdown across the three distinct recommendation models look quite different. As what the performance breakdown here shows, the operator runtime breakdown indicates diverse system bottlenecks, and this can influence our design and optimization strategies for neural recommendation acceleration. So now, if we take a broader look at the modeling techniques across the community, depending on the various use cases, the state-of-the-art recommendation model can require very different system optimization strategies. On the x-axis, I'm showing the memory intensity requirements, whereas that y-axis is the compute intensity requirements. Here, the RM1, 2, and 3 models are representative of the three distinct recommendation model categories that we previously talked about. The wide and deep network and the neural collaborative filtering model are more compute intensive. In contrast, the deep interest network consists of attention layers. These components are introduced to capture the temporal information in the training data samples. And because of this attention layers, it exposes a different degree of parallelization that can be leveraged by the particular hardware that we use to run these recommendation models. In general, we categorize state-of-the-art recommendation models into three distinct architectures. First is the embedding dominated model, and then there is the MLP dominated model versus the attention dominated models. Because of the diverse memory and computation requirements, system optimization for deep learning recommendation systems can be quite complex and challenging. It's quite obvious that one system size is not going to fit all. Finally, depending on the recommendation models and the underlying system architecture, the optimal execution configuration varies. Here, we run 5 state-of-the-art recommendation models on systems that are capable of AI accelerators, such as GPUs. On the x-axis are the different model configurations, and on the y-axis are the GPU speedup over CPUs. What we found is that the optimal configuration for recommendation query offloading depends on the recommendation model architecture. Furthermore, the degree of performance acceleration benefit can be a wide swing. to identify an optimal system configuration in this massive design space, more intelligent approaches will be required in order to take into account the dynamic execution environment in order to solve this multi-objective optimization problem. And to make it more complicated, the degree of recommendation model collocation introduces very different reactions in the tail latency response across different CPU architectures. Over the x-axis here, we increase the degree of model collocation for recommendation inference. And on the y-axis, we show the measured latency across the two different types of CPUs on Skylake versus Broadwell, highlighted in green and purple, respectively. The SIMD parallelisms between the Broadwell and Skylake processors are different, as well as the cache hierarchy implementation. On the Broadwell CPUs, it implements a mostly inclusive cache hierarchy, whereas on the Skylake CPUs, it is implementing a mostly exclusive memory hierarchy. The Skylake processors, as shown in the figure, are more susceptible to model collocation from the performance variabilities perspective. This provides much better performance predictability as well as tail latency guarantee. Next, let's take a look at the performance characterization studies across the diverse collection of recommendation model architectures on modern CPUs and GPUs. This is a recent work in collaboration with Harvard University and will appear at the International Symposium on Workload Characterization. First, let's take a look at batching's effect on speed up opportunities for GPUs over CPUs. Here, we run 8 industry representative recommendation model architectures, including Facebook's deep learning recommendation models, as shown as RM1, RM2, and RM3. Google's wide and deep and multitask wide and deep network, as well as Alibaba's deep interest network and the deep interest evolution network, DIEN. Over the x-axis, we increase the number of recommendation requests in a batch, while on the y-axis shows the execution time speed up of the various processors over the baseline Intel Broadwell CPUs. And so we look at the speed up performance for Intel Cascade Lake CPU, one of the latest generation, as well as 2 different type of NVIDIA GPUs. The GTX 1080 Ti is a higher performance GPU, whereas T4 is the new inference engine designed specifically for DNN inference acceleration. First, we want to look at how model architecture plays an important role in how much acceleration we can extract. For the models with larger MLP stacks, we observe significant speed up with GPUs. For larger batch sizes, beyond 1,000, the GPUs provide an order of magnitude higher speed up over the baseline Broadwell CPU. And for smaller batch sizes, such as those less than 100, we observe smaller speed up between 2 to 4 times. Whether this is from just fewer embedding tables in the neural collaborative filtering model or the larger FC stacks for continuous inputs in RM3 or the wide and deep or multitask wide and deep models, each of these models relies on the MLP stacks to model user preference that can be available in the data set. And in contrast, the 3 highlighted model, RM1, RM2, and the deep interest network, rely more on embedding table accesses to model user preference. For example, RM1 and RM2 have large number of lookups per embedding table for each input, roughly between 80 to 120. In comparison, the other models have fewer than 20 lookups per table. From here, we can see that the model architecture that rely on embedding lookup do not translate as well to the GPUs. And what about models that implements attention layers? From the algorithm's perspective, both DIN and DIEN use attention to learn users' evolving interests over time. However, this deep interest network, or DIN, implements local activation unit with relatively small FC layers, followed by concatenation operations to aggregate the embedding vectors. On the other hand, for DIEN, or deep interest evolution network, it implements attention using GRU, or multi-layer gated recurrent units. Because of the GRU style implementation that translates better onto regular matrix operation, DIEN usually leads to better GPU performance. However, what's really preventing further GPU performance speedup is the data communication overhead. Here we show the data communication overhead across 4 models with GPU acceleration. Again, the x-axis shows increasing batch size, while the y-axis shows the offloading overhead. As batch size increases, data communication starts becoming the dominating bottleneck for recommendation inference. In fact, for most cases, about half of the total inference time is spent on data communication. More than 50% of the total execution time for especially the MLP-dominated model spend their inference time on data communication. Going from the high-performance GPU to the inference engine T4 helps with this. And in contrast, the models with attention mechanisms spend relatively more time on model computations itself. In summary, optimal hardware can vary greatly across different recommendation model architecture and for different use cases. Across the different batch sizes over x-axis, we show that not only the optimal hardware changes from Intel's Cascade Lake to the different GPUs, but the degree of acceleration can also vary. As the batch size increases to a few thousand, this is when we start seeing the GPU acceleration potential to start pay off. What we have looked so far is when recommendation inferences serve directly on CPUs over GPUs. What happens to these performance optimization opportunity when we start considering at-scale runtime effect at the data center level? Recall, we start with hundreds of candidate items for the late-stage recommendation pipeline. When profiling the production recommendation pipeline, we find this heavy tail distribution in recommendation query sizes. This query size distribution is quite unique, especially compared to the other more known distribution used for general-purpose data center workloads. It doesn't exactly follow Gaussian or log normal distribution. As what the earlier characterization studies show, the varying query size enables performance acceleration opportunity with offloading, especially for the long tail. So now imagine a hyperscale data center with some levels of system heterogeneity, with some couple generations of CPUs and GPUs. Let's see how different model architectures perform on the GPU over the baseline CPU. Here, the y-axis shows the performance speedup with the GPU. Within each model categories on the x-axis, we compare the performance acceleration degree with a unit batch size versus a maximum batch size of 1024. In addition, we also show the inflection point with the corresponding batch sizes for when the performance of CPU and GPUs are equivalent to each other. Similar to the characterization result from earlier part of the talk, again, the MLP-dominated model benefit from GPU type of AI accelerators the most. And data communication is the primary limiting factor for GPU speedup, especially at the low batch sizes. Finally, here we consider the batch size at which both CPU and GPU platforms have equal performance. This is crucial as beyond this particular batch size that represents the number of items to rank per query, it is advantageous to process the inference query on the GPU as opposed to the CPU. In case of embedding dominated models and the MLP dominated models, this inflection point happens at a batch size of 47 and 23. Interestingly, the inflection point for the GPU to outperform CPUs for the attention model is 512. This batch size is significantly higher than the embedding and MLP dominated models. And in general, the optimal hardware platforms will depend on the type of model, the model architecture, and the size of the query distribution itself. Remember, what we care about is to maximize queries per second or QPS throughput while meeting the SLA latency target. So based on our empirical observation, the relationship between batch size and QPS throughput can often be described by this convex curve. And here we show the curve for MLP dominated model, for embedding dominated model versus the attention dominated model, such as DIN. And we show that the inflection point for GPUs to outperform CPUs varies across different model architecture. Finally, the optimal query size threshold Q varies for inference execution on CPUs because of how parallelisms can be exploited on the CPUs. More generally, we find that we can utilize a simple hill climbing scheduler to identify this optimal threshold Q. And so this is what we propose in our ESCA 2020 work. We design a hill climbing scheduler to flexibly optimize this latency bounded throughput problem by tuning batch size across different recommendation use cases. We show in the paper that there is ample room for performance and energy efficiency optimization when we take into account 4 important aspects of the design space. First is the recommendation model architectures. Second is the underlying system architecture. Third is the various runtime effects, such as the query arrival rates and the working set sizes. And then finally is the latency target specific to the recommendation use case. Now, to assess the performance and power trade-off of the proposed batch scheduler design, we propose a scheduler called DeepRecSys that models runtime query behaviors. For example, the Poisson distributed query arrival patterns and the production style recommendation query working set sizes. We evaluated the design on CPUs as well as systems that's equipped with GPUs. We also validated the proposed design in the production environment using real-time shadow traffic. Overall, DeepRecSys enables flexible performance acceleration across various use cases by looking at different model architectures, by looking at different tail latency target, dynamic application loads, using different query sizes, as well as the particular hardware platform. Here is some highlighted results. Across the different model categories on the x-axis, the proposed scheduler can effectively improve the system throughput, QPS throughput for the case of CPUs, as described by the blue bars. When we consider GPUs, we can achieve additional throughput improvement, especially for the MLP-dominated models, not surprising. While GPUs bring additional throughput gains, it may not always be the most energy efficient system target for neural recommendation. When taking a closer look at the QPS per watt comparison across the different models on the CPUs and GPUs, we found the optimal hardware that maximizes performance per watt energy efficiency for embedding dominated and attention dominated model as CPUs, while the optimal target for the GPU is for the MOP-dominated network. Okay, so overall, the proposed DeepRecSys enables flexible performance acceleration across various use cases, including model architectures, latency target, application loads, and the systems that we use to serve these recommendation models. We showed that DeepRecSys doubles the latency-bound throughput performance for CPU-based systems. And with the additional GPU accelerator, DeepRecSys can achieve significantly higher throughput by 5 times higher. When we look at the system energy efficiency, the optimal hardware target varies across different model architectures. Our production deployment experiments show approximately 30% latency reduction with DeepRecSys serving production shuttle traffic. Okay, so let's get back to my earlier points on what's going on at our research community. Why is everyone writing research papers about recognizing cats and dogs when we have a fairly important problem in the deep learning space at our hand on how to design systems for recommendation model training and deployment? If you look at the computer vision and natural language processing domain, they are standard workloads and data set that researchers have agreed upon to use evaluating their new research ideas. This, however, wasn't available for researchers and system designers to study for recommender problems. This is why I'm really excited about DLRM. DLRM is Facebook's deep learning recommendation model that was open sourced about a year ago. DLRM can be configured easily to study model architectures that we care about. For example, the width and depth of the dense DNN stacks can be varied. The number and sizes of the embedding tables can be tuned to match features found in the dataset. All of these can be changed to study, design, and optimize systems for recommender systems for both training as well as for inference. And so that's what we did. To study the effect of model heterogeneity in system design and optimization, we created a collection of 8 industry representative neural recommendation model architectures by expanding beyond Facebook's DLRM. This is a collaboration we have with Harvard University. We built an experimental infrastructure that enables us to study system design and optimization strategies for a variety of recommendation models running on a variety of systems, including general purpose CPUs to commodity AI accelerators such as GPU, and you can use it for your favorite AI accelerators as well. We make the code available on GitHub in the link shown in the slide. And on top of the DLRM and DeepRecSys, there's also this industry-wide effort to develop a machine learning performance benchmark suite. This is MLPerf. MLPerf is a community-driven benchmark standard with more than 70 industry partners collaborating with more than 10 universities. The goal here is to standardize the benchmarking methodologies, the workloads and data set used to evaluate the training and inference performance of machine learning systems. I was there since the very beginning of the MLPerf effort back in 2018 as the inference co-chair. It was immediately obvious that MLPerf was missing these important deep learning recommendation workloads in the benchmark suite. And therefore, a year into MLPerf, I started this effort to facilitate the process to bring an industry representative recommendation benchmark into MLPerf. I chair the recommendation benchmark advisory board that consists of active researchers and practitioners in the recommendation model and algorithm domain from academia as well as industry. So at the advisory board, we asked 2 important design questions. First is which recommendation model should we use for benchmarking and optimizing systems specifically for personalization and recommendation? And what data set should we be using? So it turns out that an effective recommender systems should maximize user engagement. And therefore, that's what that's defined as the performance metric in this benchmark. Furthermore, an ideal data set should include or at least capture the degree of sparsity observed in industry scale problems. And it should also cover important features like user feature, content features, or sometimes we call it item features, and the interaction between these two major categories of features. And so with the advisory board effort, lots of collaboration across the system submitters. Today, MLPerf benchmark suite includes Facebook's DLRM used to train a non-proprietary ads data set. In order to encourage more interdisciplinary research in this application domain, we take a step further to organize tutorials to advance the state of the understanding for personalized recommender systems and algorithms. We get researchers and practitioners to come together and to chime in from the perspectives of algorithm, data sets, and system designs. By doing so, we hope to come up with better ideas, solutions, innovation for recommendation systems. We also specifically, we organized 2 tutorials. The first tutorial came with more than 80 attendees. That was co-located with AskFloss 2020. And we have more than 120 attendees from 50 different organizations for the latest occurrence co-located with ISCA 2020. So now we have all the key ingredients that we need to study and build more efficient systems for deep learning recommendation models. And therefore, I hope that I've convinced you that recommendation models are important. More than 80% of Facebook's AI inference cycle is coming from these recommendation use cases. But only 2% of papers in our system research community is looking at this application domain. I've talked about a set of unique system design challenges for deep learning recommender systems. And in order to enable more research into this space, we've created new infrastructure and have standardized the recommendation benchmark and data set for our community to leverage and to study and to innovate for neural recommendation together. So where is all of these foundational systems work going to take us? And more generally, in the deep learning space. I want to sort of take a step back and think about, what we are doing in terms of what research that we are working on. How do we continue making positive impact to our society through the technical work that we work on? Great power comes with great responsibility. One of the biggest challenges for deep learning models is result explainability. Understanding AI system is very important as we also have to understand how they work and whether they work as intended. This is a topic that receives serious attention at Facebook AI research and across the research community, such that we not only understand the effect, but also begin to understand causes. For those of you who are interested in, for example, the bias or fairness aspect of machine learning dataset, I would like to point you to one of the most recent efforts from Facebook AI research on the development of ML Hub. To look at how they are these different tools that allows us to quantify fairness or biases that can exist in dataset as we develop algorithms based on these datasets. From the modeling techniques and system co-designs perspective, we have started looking at how different types of model techniques can help us explain recommendation results better. How do we make sense of the content predictions that were recommended to us by these deep learning models? How do we ensure meaningful and positive interaction? Can we and how can we leverage the information from the graph structure, for example, to explain some of these prediction results? Are there special properties that we can leverage from the graph structures in, for example, the social network graph to help us improve the interpretability of the model predictions? On the privacy front, training models with sensitive data needs privacy-preserving safeguards. One of the important opportunities for system architects is on-device AI. The significant research into enabling on-device AI is just starting to pay off. For example, neural networks running at the edge are smaller and is a lot more efficient today. At the same time, more and more neural accelerators are getting their ways into these edge systems. As what we've shown in the HPCA 2019 paper, one of the key system design challenges enabling on-device AI is the highly segmented ecosystem of the mobile SoCs. I believe this is where automatic compilation and runtime strategies are going to shine. But what is the implication of the system heterogeneity on enabling private AI? Federated learning is a good starting point in this direction. It supports training neural networks across different multiple decentralized edge devices holding local data samples. How do we make this style of distributed training approaches more robust and more efficient for the edge application while dealing with the high degree of system heterogeneity at the edge? On the inference front, we started looking into smart scheduling approach to consider stochastically varying factors, such as the continuously varying network strength that's used to connect multiple local devices together and having the cloud as the backstore. And autoscale is one of our most recent work in this direction. This is a collaborative work with my former postdoc, Dr. Yang-Guang Kim at Arizona State. Yang-Guang is now an assistant professor at Soonseo University at Korea. Autoscale is a work that's particularly timely as the 5G cellular network started maturing. With the much increased bandwidth capacity, we expect the technology to enable more and more machine learning applications at the edge that weren't previously possible. Our recent work on autoscale can accurately predict optimal execution platforms as well as processor target that could implement different bit width and therefore translates into different model quality level by adapting to the stochastic edge cloud collaborative execution environment. We've also demonstrated the proposed design on real smartphones that autoscale can improve energy efficiency of the edge device by 9.8 times over the baseline settings, while also satisfying real-time performance and model accuracy constraints. And this is done by leveraging and customizing the reinforcement learning algorithm, which is really great at understanding and predicting dynamic execution environment. Lastly, I want to highlight the impact of AI on our environment. Over the past 1 year time span from 2019 to 2020, we witnessed an 8-fold increase in the amount of computation required for machine learning model training at Facebook. Similarly, the number of parameters in state-of-the-art language models have increased exponentially, currently at over 175 billion parameters in the OpenAI's generative pre-trained Transformer 3 model, also known as the GPT-3 model. The amount of carbon emission produced by model training is quite shocking. Emma Struble from CMU showed recently that training a language model to state-of-the-art accuracy produces carbon footprint equivalent to nearly 5 times the lifetime emission of an average American car. Now, before starting off another machine learning training experiment, let's keep in mind the environmental impact each of these experiments brings to our Earth. Furthermore, this also highlights the critical importance of tools that can help us quantify the carbon footprint of AI and to measure computing's impact on our environment with a data-driven approach. The significant carbon footprint of AI also makes system efficiency optimization work especially important now. Thanks so much for your attention. I would also like to thank all of my colleagues from Facebook AI and the academic collaborators who I am very fortunate to work together on the project that I get to highlight it and share with you here. If you would like to learn more specifics about the work that I share with you, please feel free to check out these recent publications. And definitely please reach out and let's chat about ideas that you have and find opportunities to collaborate on research programs in the intersection between systems and machine learning. Thanks so much for your attention.